This is the FLSun S1, a next-generation ultra-high-speed 3D printer. It's quite unlike anything we've seen before. With its sleek appearance and impressive spec sheet, it's poised to give the competition a run for their money. But there's more to it than meets the eye. You have questions, and I have answers. Can it achieve the advertised 110 millimeters cubed per second of flow? Are the print speeds really 1200 millimeters per second, twice as fast as the Bambu X1 Carbon? And is 40,000 millimeters per second squared acceleration really achievable without loss of detail? I'll be addressing all of these questions and more, so make sure you stick around to find out the answers. But first, a message from today's sponsor, PCBWay. PCBWay is a prototyping service provider. They specialize in PCB fabrication, custom electronics, machining, sheet metal fabrication, and much more. Essentially any service that you may need to turn your ideas into reality. With PCBWay's services, you can get parts machined from aluminum, laser cut from steel, or injection molded in polycarbonate. The prices are reasonable and the customer service reps are friendly and knowledgeable. So the next time you have a project that is outside your means, remember, PCBWay can help. Alright, back to the FLSun S1. This was provided free of charge for review, and I will get a small commission if you decide to purchase one using my link in the description. But the opinions expressed here are my own, and you'll see shortly that I've been brutally honest in my assessment. So let's start with a general overview of the machine, its capabilities, and the general user experience. The S1 is a fully enclosed printer with Delta Kinematics, which sets it apart from most other printers that have either a Cartesian or Core XY motion system. The position of the carriages on the linear rails will determine the angle of the carbon rods, which in turn determines the position of the print head within the build volume. If the carriages move simultaneously up or down at the same rate, the Z height will change without affecting the XY position. If the carriages move asynchronously with relative motion between them, the XY position will change. This unique motion system has one inherent benefit and two side effects. The benefit is that we're not having to move around a heavy bed, as in the case of a Cartesian printer, or a lighter but still not insignificant gantry, as in the case of a Core XY printer. We only have to move around the comparatively lightweight printhead, which permits higher accelerations without loss of quality. The side effects are that the bed shape is round rather than square, and the printer is taller than it is wide. When I first laid eyes on the S1, I was taken aback at just how large it is. And it's got a weight to match. This thing is heavy. The quoted build volume is 320 millimeters in diameter by 430 millimeters in height. Expressed as a ratio of the overall machine volume, this is only 13%. The Bambu X1C uses 24%. So the S1 is considerably less space efficient, and this is assuming the full build volume is actually usable. In reality, the build area tapers towards the top, a consequence of Delta Kinematics. In an attempt to print a full build height cylinder, 20 millimeters in diameter, the printhead crashed at a height of 406 millimeters, well short of the advertised 430. My friend James from Cloud42 did further testing and found that the maximum height for a full build area cylinder is only 385 millimeters. FLSun does indicate this limitation in their marketing, but only implicitly, and it's not obvious how quickly the usable volume tapers off towards the top. Their own slicer doesn't account for it, meaning it will allow you to send the job with no warning that the height of your model exceeds the limits of the printer. It wasn't until I found this model on Thingiverse by a user named Serge that I was able to visualize what the build volume really looks like. By overlaying this on our model, we can know for certain whether or not it will print successfully. FLSun Slicer appears to be a mashup of Prusa Slicer and Orca Slicer. It's usable, but leaves a little something to be desired. Fortunately, an official Orca Slicer profile was recently released. To the credit of the S1 and its space efficiency, the spool holder is contained internally, rather than externally, as on most other printers, so it doesn't add to the footprint. Unfortunately, this area is only big enough to accommodate 1 kilogram spools, which is quite limiting, especially considering how quickly this printer consumes filament. There is at least a filament inlet port on the side of the printer, which could be used instead to feed larger spools from an external spool holder. The integrated filament chamber is actively heated, and has a compartment for desiccant, helping to keep your filament dry. We can set the drying time, but not the temperature. It defaults to 60 degrees, which is a little hot for PLA and a little cold for other materials. The spool holder has an internal load cell, which allows you to monitor the filament remaining on the roll. It's expressed as a percentage. An exact value in grams would be more useful, but would require that the scale be re-zeroed for each different spool type, which isn't currently possible. The interface to the printer is a very large touchscreen. The menus are intuitive and easy enough to navigate. When actively printing, a status screen is displayed providing a variety of statistics. The print speed is the most interesting, but don't be fooled. This is the requested speed, not the actual speed. The S1 can also be controlled remotely via a web interface, which uses mainsail for the front end. If we scroll over the speed, we can see just how different the real speeds are from the requested ones. Even though the printer is being told to print at these high speeds, it never actually achieves them. Keep this in mind for later. We'll come back to it. The S1 is equipped with an onboard camera, oriented in portrait mode. This is used for remote monitoring and time lapses, as well as AI failure detection. Time lapses are stored in internal memory and can be viewed directly from the screen. They can't, as far as I can tell, be viewed through the web interface. In order to get them off the printer, you have to manually download them to a USB. If you don't do this before recording a new one, the old one will get overwritten. So the functionality seems kind of half-baked. From the screen, we can toggle on and off various detection settings, including spaghetti and debris detection, first layer inspection, and clog detection. In my testing, the system successfully detected multiple spaghetti events, pausing the print and awaiting user intervention. In one instance, the filament broke within the PTFE tube, which registered as a clog. The printer paused and allowed me to unload and reload the filament before resuming. The first layer inspection uses LIDAR. The chamber lights are turned off and a line laser is turned on. The printhead then scans to detect abnormalities. The same approach is used for two other functions: flow calibration and precision calibration. In the case of the former, 4 lines are printed with different thicknesses. In the case of the latter, a rectangle is printed. The laser is then used to gauge the thickness of the lines or the width of the rectangle. These two calibrations should, in theory, adjust the flow rate and scale compensation for future prints, such that you are not under or over extruding and the results are dimensionally accurate. In my testing, neither worked as intended. Rather than scanning, the laser would just stay in one location for a long time before jumping to a new spot. Upon completion, the printhead would rise and crash into the bottom of the filament dry box, causing the calibration to fail. The precision calibration would complete successfully, but produced a seemingly incorrect measurement. When measured with calipers, the width was much closer to the target value than the laser seemed to indicate. It's also unclear to me where this value is stored or how it can be adjusted. Normally, you'd expect to see any saved variables at the end of your printer config, but there's no sign of the results from any of the LIDAR calibrations. Hopefully, all of this functionality will be fixed in a future firmware update, because it would be really nice to have, but for now, it's unusable. The S1 runs Klipper firmware, but FLSun has layered a ton of their own functionality on top of it. This sounds good in theory, but it's not without its faults. The touchscreen will often get out of sync with the web interface. The only way to fix it is to power cycle the printer. There are also certain parameters that you can't view or edit as you normally would in Klipper, including anything to do with the LIDAR or AI functionality. One feature that just doesn't work at all is pressure advance, and there's no LIDAR-assisted automatic calibration for it as there is on the Bambu Lab X1 Carbon. An attempt to do manual calibration using Orca Slicer to generate the G-code yielded a null result. There was no visible difference in the seam over the entire range of test values, so there's no automatic calibration and no way to calibrate it manually. The seams don't look terrible using the default values, but they could definitely be better, so it's disappointing that there's currently no way to tune this. There's 2 other automatic calibrations that do work as intended, those being bed mesh generation and resonance identification for input shaping. The nozzle is used for probing, meaning that the Z offset is calculated automatically. This is convenient, assuming the nozzle is clean. There's no nozzle wiping brush to deal with filament ooze, as on other printers, so that makes it error-prone. The Z offset can be adjusted from the screen, but for some strange reason, they put an upper limit on the adjustment. What's worse is that the offset appears to be temperature dependent. The hotter the nozzle, the closer it seems to be to the bed. When printing at PLA temperatures, the offset is reasonable. When printing at ABS temperatures, it is far too close, with the necessary adjustment exceeding the permitted range. To correct for this, I tried hard-coding an offset in the slicer, but it just seemed to ignore it. So for now, the only option is to manually override the Z offset in the printer config, updating it every time you switch between high and low temperature filaments. Visualizing the bed mesh reveals that the bed is far from flat, with a range of 0.6 millimeters in the measurements. Unlike a traditional bed with origin in a corner, the origin is at the center, and it's clear from the shape that the printhead is suspended at 3 points. Despite this result, the first layers were perfectly adequate in my testing. The default first layer of speed of 200 millimeters per second is faster than most printers print infill, which is absolutely wild. Although I found I needed to slow it down in order to get better results. The final calibration, input shaping, works similarly to other printers. The printhead vibrates in order to determine the resonant frequencies. Since the X and Y motion are coupled and not independent, there is a single global setting for the shaping function and frequency, unlike on a Core XY, for which each axis is unique. At this point, I'd normally SSH into the printer to download the shaper graphs and visualize the frequency response. Unfortunately, the SSH credentials for the S1 are not currently public. When asked, an FLSun rep told me that they'd be released eventually, but it's not clear when. With all of the calibrations out of the way, let's get to printing. There's two things you'll notice right away. The speeds are fast, like insanely fast. And the fan is loud, like insanely loud. Rather than having a fan mounted to the printhead, the S1 has a centrifugal blower installed up top, with the air routed through a CPAP style hose. This can definitely move a lot of air, but it sounds like a vacuum cleaner when it's running. It's so loud, in fact, that you'd be wise to wear hearing protection when you're in its vicinity. In an effort to reduce the noise, FLSun has designed a silencer which is pre-sliced and ready to print from the onboard memory. Despite looking more like a holiday decoration, it does its job effectively. There's a notable decrease in noise levels with this installed. But does the cooling performance of the S1 match the print speeds? Sometimes, but not always. On shorter layers, the cooling is still insufficient. The fan moves with the printhead, so the airflow isn't always being directed where it's needed most. For this reason, an auxiliary part cooling fan with a static position would be more effective. It provides a constant stream of cool air to solidify the molten plastic quicker. The S1 doesn't have one, so the only solution is to implement a minimum layer time in order to give the plastic enough time to cool between layers. This helps with cooling at the expense of print speeds. Even with the silencer installed, the S1 is louder than an average printer with the fan at 100%. But it's also at least 2 times faster, so you may be willing to live with the noise. A comparison of slicer time estimates reveals just how much quicker the S1 can complete a print relative to the alternatives. This Prusa rocket engine model had a slicer estimated print time of 4.5 hours. In reality, it took 5.5. The same model printed on the Prusa XL takes over 15 hours. The torture toaster by Clockspring takes 2.5 hours on the S1. On the Bambu X1C, it takes 5.5 hours. This adjustable table leg took 1 hour and 40 minutes on the S1. On the X1C, it took 3 hours and 22 minutes. So that all sounds pretty impressive for the S1, but it's not enough to compare print times without also comparing print quality. The rocket engine honestly looked flawless. The layers were well stacked with no visible banding. The overhangs were sharp with no drooping, and the overall print quality was clean with no zits, blobs, or other defects. Mind you, this was printed in Prusament Galaxy Black PLA, a high-quality filament with a matte finish, which prints well and looks good on most printers. Glossier filaments printed on the S1 do show some signs of VFA, or vertical fine artifacts, with a characteristic pattern that seems to trace the swing of the carbon rods. I've seen reports from other reviewers indicating that they observed severe VFAs, with some attributing the phenomena to the stepping pattern of the closed-loop motors. In my experience, the VFAs were no worse than I've observed on other printers, just different. In general, layer stacking consistency is very high with good surface quality. Now let's look at some more challenging models. I first attempted the torture toaster with some run-of-the-mill bargain brand PLA. The overall quality looked pretty good, with particularly good performance on the overhang test and the top solid layers. However, only one piece of toast would pop, and the tolerance test failed at a disappointing 0.3 millimeters. I then reprinted it using the supplied high-speed PLA. This time, both pieces of toast popped, and overall the quality was better, but I struggled to free the 0.3 millimeter tolerance test, breaking it in the process. The same model printed on the X1C actually scored the same in the tolerance test, but performed considerably worse on overhangs. The print quality on this table leg was only okay. The seam was quite prominent, and there was a pattern on the outside of the print that matched the internal threads. The same model from the X1C wasn't great either. The seam was better, but still prominent, and there was also a fair amount of ghosting, banding, and other surface artifacts that detracted from the overall quality. The major difference is that the part printed on the S1 was easily broken with a little force, whereas the one from the X1C couldn't be broken no matter how hard I tried. The loss of strength at increased print speeds can be counteracted by increasing the temperature, within reason. But it's clear from these results that the supplied profiles are optimized for speed, and not strength or dimensional accuracy. Speaking of, let's print a cauliflower to see how it fares. If you're not familiar, this tests how square the motion system is on your 3D printer, using a series of measurements to quantify the skew of the axes. It can also tell you how close the printed model is in size to the target value. There was some feedback on my first video about the S1, indicating that Delta printers generally aren't very square, and it's easy for them to get out of alignment. I can't say that I understand why that's the case, but armed with this expectation, I was anticipating a less than optimal result from the cauliflower. As a baseline, I also printed one on the X1C, with a result of 89.9 degrees for the angle between X and Y, with 90 degrees being optimal, of course. The S1 measures 90.03 degrees, making it surprisingly more square than the X1C. I don't know for certain, but this result defying expectations could have something to do with the fact that the S1 has closed-loop stepper motors. The X1C and nearly every other printer use open-loop control, meaning that there's no feedback loop between the position requested by the firmware and the actual position of the motors. The S1 has a PCB on each motor that is actively monitoring its position. These should help keep the axes in alignment while also preventing layer shifts. Dimensionally, the cauliflower measured an average of 0.35% undersized. This was consistent with my previous observations. Every tier on the tower of the Autodesk Kickstarter FDM benchmark measured smaller than the nominal value. In order to correct for this, we can set the XY scale compensation in the filament settings for Orca Slicer. Since the automatic flow calibration wasn't working, I also used Orca Slicer's built-in flow calibration tool to determine the optimal flow rate. Based on my findings, the default value had it under extruding by almost 10%. So the S1 won't make dimensionally accurate parts out of the box without considerable tuning. Alright, I think I've kept you waiting long enough. Let's run a max flow rate test to see if the claim of 110 millimeters cubed per second is justified. Starting at 20, this racetrack test increases the flow by 0.5 millimeters cubed per second for every few millimeters of Z height. If the claim is true, the entire tower should print without issue. Things were going well at first, but then it started to fall apart. The extruder started skipping at nearly 30 millimeters cubed per second, less than a third of the advertised value. That is nearly double what I measured for the stock hot end on the Bambu X1C, but it's a far cry from 110. So what gives? I reached out to FLSun to provide them with my findings. In response, they provided the G-code they used to validate this claim. Importing this into a G-code viewer, we can see that it does appear to test a range of flow rates all the way up to 110. So let's see how it prints. It started to under-extrude near the top, but not drastically. So can it print 110 or can't it? Remember how we talked earlier about requested speeds versus actual speeds? The same applies to flow rates. It's one thing to ask the printer to achieve 110 millimeters cubed per second of flow, but it's another thing for it to actually do it. In order to reach those flow rates over such short distances requires high speeds and high accelerations. Mousing over the flow rate statistic for the active print reveals that the maximum flow rate achieved is only 57 millimeters cubed per second. And as we can see, the quality starts to degrade before then. Upon inspecting the G-code for this test, I noticed that the accelerations are set to a meager 2,000 millimeters per second squared. So there's absolutely no way this was even attempting to hit a flow rate of 110. If this is the exact test FLSun used to determine the max flow rate, which I'm told it is, that's a real problem. At best, they fooled themselves into thinking these flow rates are possible. At worst, they knew what they were doing. Let's give them the benefit of the doubt and assume it was an honest mistake. But it really doesn't look good when they've leaned so heavily on this artificial number in their marketing. So we've debunked the flow rate claim. What about their claims of 1200 millimeters per second print speeds and 40,000 millimeters per second squared accelerations? Well, let's be clear. There's a difference between print speeds and travel speeds. 1200 millimeters per second are the travel speeds. Print speeds top out at 800 millimeters per second, which isn't 1200, but is still impressive. In contrast, the Bambu X1C travels at 500 millimeters per second and prints at a max speed of 300. The time savings for travel moves on the S1 is considerable. The X1C spends a total of 25 minutes traveling during this print. The S1 only spends 7. Lastly, let's evaluate the acceleration claim. The acceleration limit in the firmware is 40,000. However, in the print profile, the maximum acceleration is 32,000 for travel moves. For normal printing, the acceleration is capped at 30,000. This is 3 times higher than the 10,000 on the Bambu X1C, but only 3/4 of the advertised value. So in summary, the speed claim is true with an asterisk. It applies to travel, not printing. The acceleration claim is embellished, and the flow rate claim is downright false. The hot end, while impressive, still must adhere to the laws of physics. It's got a cylindrical ceramic heater. The nozzle is nickel-plated copper with a hardened tip, giving it a good combination of abrasion resistance and thermal conductivity. What's really interesting is what's inside. Instead of having the specialized internal CHT geometry for better melting performance, this is just a standard V6 nozzle. It's not even a volcano. There is, however, a CHT-style geometry inside the main body of the hot end. I'm assuming this unique approach is their way of circumventing the patents of 3D Solex, but I could be wrong. Somewhere inside this printhead is a dual-gear direct drive extruder. I say somewhere because it's inaccessible without significant disassembly. The same goes for the hot end. It's all very tightly integrated. FLSun has a tutorial video you can follow, but if you ever need to access them for maintenance, it looks like it'll be a headache. I'd classify this as a major shortcoming of the design. Ease of maintenance is very important for the longevity of a printer. As compared to the Bambu X1C, on which the hot end and extruder can be easily accessed, the S1 falls well short. There's also currently no inventory of spare parts. On the bright side, FLSun has taken a page from Bambu's book and is building out a wiki with information and guides on how to maintain the printer. There's still some information missing, but it's a good start. In addition to what we've already discussed, the S1 has 2 more features that set it apart from the competition. The first is a segmented heat bed. This enables zone heating, which is intended to conserve energy by only heating the part of the bed that is necessary based on the size of the print. This is nice, but not something you'll actively notice or appreciate unless you're keeping track of your electricity bill. And even then, the impact will likely be small. When they first announced the equivalent feature on the Prusa XL, I thought it meant that the bed would heat quicker, allowing prints to start sooner. In reality, a long heat soak period is enacted, which negates any time benefit of the zone heating. The S1 doesn't do a heat soak, but it also only has 2 zones and not 16 as on the XL. The final feature worth mentioning is the integrated UPS, or uninterruptible power supply. This should allow the printer to keep printing in the event of a short power outage, or at least park the hot end away from the print. Power loss recovery is a common feature on most modern printers, but in the event of a power outage, power is cut immediately. When the power comes back on, the printer will prompt the user to restart the print. But by this point, the bed has likely cooled down, causing the print to detach and rendering the job unsalvageable. With the UPS on the S1, the printer could still have power for up to 30 seconds after an outage. If the power is restored within that window, the printer could keep printing as if nothing happened. At least that's how it should work. In practice, like many of the other advertised features, it doesn't work as intended. I simulated a short power outage, and not only did it not keep printing, it didn't offer me the opportunity to resume the print. If the power stays off long enough, the printer will shut down completely. Upon restoring power, it will ask if you'd like to resume the print or not. It will then rehome and attempt to continue printing. Unfortunately, in my testing, it never did so successfully, with the nozzle appearing to be clogged. So by now, you should have a really good sense of what the FLSun is all about and what differentiates it from the competition. It's got a lot of bells and whistles, but not all of them work as intended. Initially, the ridiculous flow rate of 110 was set in the profiles for every filament, from PLA to PTG and ABS. Unsurprisingly, this led to poor results, particularly with a filament like PTG, which just doesn't flow as well as PLA. In a later update to their slicer, FLSun reduced the flow rates for all filaments but PLA to much more conservative values. This gives better print results, but increases print times to the point where they are comparable to other, slower printers. I tested TPU as well, and I'm happy to report that it can print it, but don't expect to take advantage of the high print speeds. I was able to print faster than average with a volumetric flow rate of 5 mm3 per second, but anything higher than that caused the filament to bind in the extruder. With a max nozzle temp of 350 and bed temp of 120, the S1 also has the potential to print engineering-grade filaments. What it lacks is a heated chamber. With just the passive heating from the bed, the chamber temperature reached the low 40s after about 30 minutes. This is usable for smaller parts, but less than ideal for ABS, let alone PC or other high-temp materials. Heat rises, which is to the disadvantage of the S1, as it will move quickly out of the usable print volume and into the area occupied by the spool. The X1C, with its descending bed, benefits more from the thermodynamics of convection. The warm air stays with the print. It's also just a smaller enclosed space, which allows it to reach a higher chamber temperature with only the passive heat from the bed. With chamber heaters appearing on other, less expensive printers, it's disappointing that the S1 doesn't have one. What it does have is chamber cooling, which is just a fancy way of saying there's an exhaust fan. This is intended to blow heat out of the chamber when printing PLA, and features a combination HEPA and active carbon filter to clean the outgoing air. This air filtration is more necessary when printing ABS, but it will be at the expense of conserving heat, so you'll probably prefer just to leave it off. The other limiting factor in the S1's ability to print engineering-grade materials is the heat block. The nozzle may have a hardened tip, but the heat block is aluminum. Running abrasive materials through this will eventually eat away at the metal, so you won't be able to print carbon fiber or glass-filled composites with the S1. This is a shame, because those additives tame otherwise warp-prone materials, making them more printable without a heated chamber. Alright, I think that covers all of the features. Let's summarize the positives and the negatives. Starting with the negatives. Large footprint relative to build volume. High operational noise levels. Internal spool holder is size limited. No temperature control for drying functionality. Inconsistent Z offset, especially at elevated temperatures, making ABS printing unreliable. Flow multiplier and precision calibrations don't work. No flow dynamics calibration, and pressure advance not working. Poorly tuned print profiles. Finished parts are weak, with poor tolerances. No heated chamber. No auxiliary part cooling fan. Confusing firmware. Klipper layered with FLSun specific features. False advertising on max flow rate. Misleading advertising on max speed, max acceleration, and max print height. No SSH access. Yet. Maintenance is extremely difficult. Time-lapse implementation is half-baked. Power loss recovery not working. UPS makes it worse rather than better. No AMS for multicolor support. And it can't print abrasive materials. On the positive side, good aesthetics. Nice user interface. Print times are approximately half those of the Bambu X1C. Good print quality, especially vertical surfaces and particularly with matte filaments. Closed loop steppers, no layer shifts. Integrated filament dryer. High max nozzle temp and bed temp. CPAP cooling. Convenient AI features. Clog detection and spaghetti detection. Standard V6 nozzle, not proprietary. And finally, it's running open source firmware, Klipper. If you had to summarize all of this in one sentence, it would be this. The S1 is great for art, but not engineering. It can print some great looking PLA models in record time. But as soon as you try to print in an alternative filament, or need something with good tolerances, things start to fall apart. I don't doubt that it's possible to get dimensionally accurate and strong parts from the S1, but it will require slowing down the speeds considerably, and doing a lot of your own tuning. So that's been my coverage of the FLSun S1. I definitely like it, and it will have a place in my workshop, but I'll be reserving it for aesthetic models or quick and dirty prototypes. But I'd love to know what you think. Let me know in the comments down below. Thank you so much for watching. If you enjoyed the video, please give it a like and consider subscribing. My name's Taylor, this is Y2K3D, and until next time, happy 3D printing.